Now we're going to look at relative density, expansion and combustion. You can actually see right on the front here really how sort of density, expansion and combustion can all have an effect on each other. You can see here your flame, which is combustion, causing an increase in temperature of water, which causes it to expand. That as it expands, it also reduces in density because the molecules, as they expand, they move away from each other. Density is essentially mass by volume. So the smaller the volume, if you have an equal mass, the greater the density. If you have the same mass but a larger volume, the density will be less. It means the molecules are further apart when it's less dense and closer together when it's more dense. Relative density means something a little bit different, and we're going to sort of talk about that as part of the session today as well. Okay, so into this part of the session, I want you all to be able to describe 3 things that are essential for combustion to take place, and state the combustion temperatures and calorific values for natural gas, butane and propane. Also, I want you guys to tell me how temperature can affect expansion, including calculating the effect, calculating how much things will expand when they're heated by a set amount. Also, I want you guys to be able to compare the density of solids and liquids to water and predict whether they'll be able to float or sink, and also do the same with gases, with air, and predict whether they'll rise in the air or fall. So, as we've mentioned before, when materials are heated, they expand, they get bigger. And when materials expand, they also become less dense. And we'll explore this in the session alongside looking at the generation of heat through the burning of fuels. So, for anything to burn, it requires 3 things: fuel, oxygen, and the source of ignition, or sometimes people might say fuel, oxygen, and heat. And different fuels burn at different temperatures. Generally speaking, sort of LPG gases, which are gases, for example, like propane, butane, or MAP, have got a combustion temperature of around about 1970 degrees C. Natural gas burns at a slightly lower temperature, made up mainly of methane. It's got a combustion temperature of around 1920 degrees C. Whereas kerosene actually burns a fair bit of a higher temperature, and the high burning temperatures of these make all of these good fuels for boilers. In fact, most boilers are natural gas boilers. They run on mainly methane, but you can also get sort of LPG boilers and oil boilers as well, which would sort of run on kerosene. And each of these materials, each of these fuels will have a different calorific value, and essentially the calorific value refers to the amount of energy that's released when it's completely combusted. Calorific values can be measured in megajoules per meters cubed, and as we've mentioned before, joules is energy, isn't it? So millions of joules per meters cubed. So the some key info to remember here: natural gas made up mainly of methane. There are some other gases in there. It's lighter than air, and it's actually got a relative density normally of between 0.6 and 0.8, average at 0.7, which means that it's sort of 0.7 of a times the weight of air, which means it's lighter than air. It would rise in air. And it's got a combustion temperature of 1920 and a calorific value between 38 to 39 megajoules per meters cubed, depending on the sort of the mix that makes it up. LPG is made up of any mixture of propane, butane, or MAP, or any of those individually. MAP stands for methyl acetylene propylene propane. Each of these are heavier than air. Butane's roughly twice as heavy as air, I think propane's about 1.5 times as heavy as air. MAP I'm not sure about off the top of my head, but these have got a very high calorific value. They've got a lot of energy in them per meters cubed. 95 megajoules per meter cubed for propane, or 121 megajoules per meter cubed for butane, which is a huge amount of energy per meters cubed. And its combustion temperature is a little bit hotter than natural gas at 1970 degrees C. So what happens now when materials are heated, if we use this energy to heat materials? Well, we'll find that most materials will expand when heated, and how much they expand depends on their makeup. So as things heat up, the molecules generally move further apart from one another, which means they become less dense, but they also become larger and longer. And as the materials cool, the molecules move closer together, and the material then becomes more dense and shorter and smaller. And how much it expands actually depends on the coefficient of linear expansion for the material. And we can calculate it by taking the length in meters, multiply it by the temperature rise, and then multiply that by the coefficient of linear expansion. But the key thing to remember, okay, is plastic, like for example PVC, ABS, polybutylene, polyethylene, any plastic will expand many, many times more than any metal. The plastic expands a huge amount more than metal, and that's worth remembering, because they do like to ask about that in the test, okay? So the coefficient of linear expansion for a lot of materials are known, and some of them are shown on the right just here. Okay, and this is how you do the calculation. Just for example, we've got, say for example, we had 6 meters of a plastic discharge stack, for example, which is heated by 19 degrees C. We know that from the last page, the coefficient of linear expansion for plastic is 0.00018. So we times coefficient of linear expansion by the temperature rise, 19, times by the length, which would then give us an answer in meters. In this case, it gives us an answer of 0.02052 meters. We can then change that to millimeters by timesing it by 1,000. So if we move that decimal point, 10, 100, 1,000, we've then got 20.52 millimeters. And we need to take this expansion and contraction into account in plumbing systems, and that's part of the reason why we leave that expansion gap in our guttering fittings of 10 mil. So if we don't take that into consideration, our components will be damaged, they may start to break down and start to leak. Okay. Now we're going to look at density. Density is by definition the ratio of mass to volume of a body, and you can calculate it actually by taking, you can calculate the density by dividing the mass by its volume. And the SI measurement for density is kg m3, kilograms per cubic meter. And as I've mentioned previously, if you heat something, it gets larger, moves apart. So when you heat it, it also lowers its density. When it cools, it's going to contract, the molecules will move back closer together, and that means that it will increase in density generally as it cools. And it's also worth being aware of relative density. And relative density, sometimes known as specific gravity, is actually, it's a different way of measuring the density of a substance. And you do that by comparing it to water. You compare the mass of the object to an equal weight, normally of water, if it's a liquid, or if it's a solid, or an equal volume of gas you would compare to air. And if, for example, we had 1 meters cubed of air and 1 meters cubed of butane, you'd actually find that the butane would weigh twice as much as the air, 2 times as much as the air. So therefore, that would have a relative density of 2 because it's twice as heavy as the air. That would also mean that if you put air and butane in together, the butane would fall towards the bottom of the container, and the air would sort of then push the air up. Propane is 1.5 times heavier than air, so again, if you put the propane in with the air, the propane would fall towards the ground. Any LPG gas is heavier than air. Methane is, or natural gas, is a little bit lighter than air. It's got a relative density of 0.6. So if you put methane in a container with air, that methane would rise to the top. So it's between 0.6 and 0.8, depending on the makeup of the natural gas, because there's other gases mixed in with the methane as well. And yeah, it's the same principle is true with water. For example, if you dropped a bar of copper into water, it would sink. That's because its relative density is 8.9. It's actually 8.9 times heavier than water. If you had 1 meters cubed of water, 1 meters cubed of water weighs 1,000 kilos at 4 degrees C, and you had 1 meters cubed of copper, that 1 meters cubed of copper would weigh 8,900 kilograms because it's 8.9 times more dense than water. Okay, another example, aluminium. Aluminium's 2.7 times heavier than water. So if you had 1 meters cubed of aluminium, it would weigh 2,700 kilos, because we know it's 2.7 times more dense than water. So if you dropped aluminium into water, it would sink. If you then poured some fuel oil, for example, Class C fuel oil, you can see here, it's got a relative density of 0.79. That's less dense than the water, so then that fuel oil would then float on the top of the water. And you can see a nice example here. You've got some water here with sort of various substances in there. They've put some gold in there, and the gold's the most dense, so that's going to fall all the way to the bottom, with mercury on top. Again, it's dense, but it's not quite as dense as the gold, and lead slightly less dense than the mercury, so that would sit on top of the mercury, but it's more dense than the water, so it still sits towards the bottom. And then you can see then our oil, which is less dense than the water, sitting on the top, with cork, which is the least dense out of all of the substances we're looking at here, floating right on the top of the oil there. And you can also see the same thing happening in air. We know butane's got a relative density of 2, so it's heavier than air. If you put that in a balloon, it would sort of sink in air. And methane is a bit lighter than air, so therefore if you put that in a balloon, it would then sort of float. Alrighty. One thing worth noting, okay, propane and butane, as we've said before, are both more dense than air, both heavier than air. So you need to be very careful if you work with them, because they, particularly in excavations, because they're heavier than air, they'll sort of fall down and they can collect at ground level and could build up to explosive levels. So just be very careful. Yeah, one thing worth noting, I kind of touched on this a little bit earlier, but if 1 meters cubed of water at 4 degrees C has a massive 1,000 kilograms, well, it does, that's how much it'll weigh. 1 meters cubed of mild steel is a massive 7,700 kilos. We could then calculate what is the relative density of the mild steel, and to do that, we'd divide the mass of the mild steel by the equal volume of water, which could then give us a relative density which is 7.7. So we've got equal volumes here, so 1 meters cubed and 1 meters cubed. So we take the mass of one, divide it by the other, and that gives us the relative density. Okay, so we can see the same volume of steel and water. The steel is 7.7 times heavier, so therefore it has a relative density of 7.7. Okay, now it is time for your task.